Good morning, folks. How you going? Another very cold morning here in Canberra. Might move my music stand. Whoop. So I get a little bit more green screen space. How's everybody going this morning? Welcome to week 9 for COMP2300. Today's lecture is going to be mainly about networks. That's the topic of this week. Let's make sure my mic is working. That should be fine. I should make sure I'm recording as well. All right, now I'll start again. Welcome everybody to COMP2300 for week 9. Today's topic is networks. We've now, I guess, gotten through the technical content for COMP2300, and the technical content by which I mean all the stuff which is focused on doing things practically with your disco board. I think we still make contact with your disco board in the next few lectures, but we've got a few, I guess, higher level topics to get through over the next few weeks. And the first one is kind of a high level view on how computer networks might work this week. And then next week we have a kind of high level view about how operating systems might work. And then in week 11, a higher level view about how CPU architectures work. And so these three topics, I guess, they're a little bit of a tour. We do only an overview of each one, and that would be kind of a bit of a taster for you to maybe take a more specialized course in operating systems or networks or architectures later on in your degrees. But before we start exactly with the network stuff for today, I wanted to just finish off a few points about how you can use these synchronization primitives on your disco board, the synchronization primitives which you get. And you remember last week we were talking about this problem when you are able to do a context switch on your computer. Once we're able to take our program and using an interrupt, kind of pack that whole program context away, put it away in memory, and grab some other program context and bring it all the way back in. And that led to a few problems. The main one being that if we were sharing memory between multiple programs on your disco boards, both programs of course can access it. We have no way so far of stopping some other program accessing memory. But more problematically, if one of these programs gets switched out and comes back, there's no way for it to know that that's happened. It can't even comprehend the fact that it's been switched out. It's just waking up as if nothing had ever happened, looking in memory and assuming it's all fine. And we could see very clearly that another process may have changed some memory while the first process was asleep. And then by the first process continuing with its writes or reads or whatever it was doing, it's going to get very confused and lead to unexpected results. So we talked last week about various ways that you can address this problem, and a number of different hardware level, instruction level solutions to this. And one was that idea of having atomic operations that do two things at once, like they switch out a register and a address in memory or swap them over. One of them that tests a address in memory at the same time as writing to it. So you can use these atomic operations to implement a lock or a mutual exclusion, and then use those structures to then get higher level synchronization schemes like semaphores, which we discussed. It is a lot like split personality, Adam, but I guess the split personalities each have to have a bit of a discussion or have some kind of protocol for remembering which one's in control. So at least the way the movies portray it. Now, we've got a few more slides to go through for this topic, just to basically really nail down exactly how this works on your disco board. And not that it's something that you particularly need to do in any of the assignments. The closest you get to this topic is when you're doing labs 11 and 12, or week 11 and 12 lab, which asks you to design your own operating system, which is certainly an interesting thing to consider that would be even possible for you to do. So on your disco board, you get these two operations, literx and stirx. So literx, it just looks almost exactly like liter, the regular old memory reading operation. So we're going to start, I'll make myself small, sorry. We're going to start by loading in some kind of memory address. We're going to get this label in data section, some memory address, into R0, and then I'm going to get that data into R1. So far, so good. Nothing special happening here. Now, when literx does this, it also sets something called the local exclusive monitor. This is the way it works on your disco board. It's a very, by comparison with other systems, it's a simple processor in the ARM v7M line. The Cortex-M processors are simpler than ones that might work on a Raspberry Pi or on a mobile phone. So this local exclusive monitor can only store one bit of information, and it's just like a little tag, and it's either going to represent open or exclusive. So when you've done a literx, it sets it to exclusive, and if you haven't done the literx, it's normally open. And it doesn't check that little monitor before it does anything. It just sets it to exclusive. Now we have the second operation at the other end. We do, just to say that more advanced processors that might have multiple CPUs on the same, or multiple cores on the same CPU, also have another monitor called the global exclusive monitor. So we're not talking about that here, we're just talking about the local exclusive monitor. At the other end, when you're doing an exclusive store, here's the same operation. I'm going to get my memory address, R0. I'm going to put 5 into R1, and I'd like to store 5 into this memory address. So I'm going to go stirx R2, R1, in brackets R0. So R1 is what I'm storing in that memory location in the brackets, and R2 is where I'm getting a little message back from exclusive store. So the storex is trying to store R1 in memory that R0 is pointing to, but it's going to check the exclusive monitor first. And if the store is allowed by this exclusive monitor, then R2 is going to be set to 0. And if the store is not allowed, then R2 is going to be set to 1. So this is our sort of success bit, our success register. So then after that, we can compare R2 with 0, see, did this store actually work? And if R2 is 0, that means it worked. If R2 is not 0, it didn't work. So B and E, we have to do something else to recover, probably go right back to the top and try the literx and storex again, try the whole sequence. So it's a little bit complicated. If you look in the manual and start to try to unravel this, it's a little bit complicated to work out when the stirx can actually fail. So if the local monitor is tagged exclusive, then the store takes place, stirx works. And if the local monitor is not tagged exclusive, then it's implementation defined whether the store takes place. So we can find this out just by doing some tests with our disco board in a minute. But when we go into these deep, dark manuals for CPUs, it starts to get a bit frustrating when there's a lot of implementation details that are not apparently clear. And then a little bit more detail about this exclusive monitor. There's actually 3 operations that we're interested in. There's another one called CLRX, ClearX, which just opens the exclusive monitor. It doesn't do anything else. That's our 3rd interesting instruction. Here's a little state diagram for our, our exclusive monitor. It's either open or exclusive. So every time we do an exclusive load, I'll just use my pen here, why not? Every time we do an exclusive load, then we go from the open state to the exclusive state. Then if you do more exclusive loads, it stays in the exclusive state. If you do just regular stores, it's probably going to stay in the exclusive state. It is going to stay in the exclusive state unless in some cases it doesn't. But that's, again, implementation defined, I guess. And if you do an exclusive store after that letter X, then it opens access again. So load exclusive will close it or put the tag on, exclusive access, and then store exclusive is going to take the tag off. So they work as a pair. And whatever you do, if it's exclusive, the clearx operate instruction will open that tag. And if you're already open, then clearx leaves it open. So I guess that's a little bit of a complicated diagram. I was trying to work out for myself how this works last year, looking deeply in the manual, and couldn't quite get it right. But I think that the crucial thing to recognize here is that on your disco board, in this system, the local exclusive monitor is just 1 bit. There could be other ways to design this, where you maybe have a monitor which stores the address that you're interested in or the region of memory that you're interested in, and that could have a sort of more advanced version of this same operation. But in our case, we only have a very simple, or the simplest possible way of doing it. And it turns out that that's all we need. We just need that 1 bit to be able to keep track of whether we've been frozen in carbonite and woken up, or whether we have not been and can continue doing our memory operations safely. So there's nothing like just giving this a try, is there? So here's a program. And I've got a few words in memory. And I suppose I'm going to get equals Charles word. I'm going to get the this is going to make sense. I think I'm going to just try loading up one of these words in memory, and then I'm going to grab, try to do an exclusive load, an exclusive store, and we'll see what it takes to mess it up. So that's my my plan so far. So I'm going to grab the address of my word, oops, and then I'm going to do a letter X, R0, R1, R0. So I'm going to just make sure I've got my other thing on so people can yell at me in the chat. There's separate local exclusive monitors for separate values. I think Adam might be asking if there's separate local exclusive monitors for each memory address. No, there's only one. There's 1 bit of information to keep track of this for your whole disco board. It's funny that that should work, right? But you can do these implementations just with that 1 bit. So we're doing our letter X. Basically, I have to wait in the chat until Benjamin Gray shows up as well, so that he can tell us all exactly how it works in v7m. The emulator man has to be present for complete assurance of the way things work. Okay, so I've loaded my value into R1, and I'm just going to add R1, 1. Why not just increment it? And then I'm going to stir X back again. Okay, and I want to over here, R2 is where I'm going to get the result of my store, as in whether it was successful or not. So I can compare R2 to 0, then BNE, and I'm going to make two loops. So I'm going to have down here something called failure loop B up. And the creatively named success loop. Need a space. Okay, so if things work out, I should be in the success loop, and if they don't work, I should be in the failure loop. So if it is 0, then we should be going to the success loop. And if it's not 0, we should be going to the failure loop. Okay. Cool. I'm gonna. Let's run this and see how it works. We'll see if it works. Hopefully it works so far. Adam, we're just talking about in the chat about the single bit for checking how this works. It is surprising that it's so simple. It really is. I'm sure that the first thing to remember is that the hardware, I guess, would be intended to be as simple as possible so that then you can build more complicated structures on top of it. Second of all, we're in a very simple CPU. So we're not dealing with, we have no memory management unit, we're not dealing with virtual memory, we're not dealing with cache so much as we would expect to be. We're not dealing with multiple cores. We're not really expecting to run an operating system on this CPU. So there's a lot of things about the Disco board which are designed to be simple because it's supposed to be low power, it's supposed to be for embedded operations. And in other situations, it could be different. So here's my program. Let's see if it works. I get my expected address in R0. I load 0 into R1. Then I'm going to increment that. And then I'm going to store it back. And R2 is going to have my success or failure value. So it's 0. So that means it successfully stored it back. Now I do the compare. R2 is 0. And I should go into the success loop. Good, so it was successful. Everything works out. Now, so far we know what we're doing, but we know that at any time we could have some kind of interrupt or something happens. And I'm not going to do actually triggering an interrupt. I think that would be just a bit much for right now, but I'm going to do the next best thing, which is to have a fake interrupt handler function that suddenly shows up. So I'm going to have a function called another task, bxlr, always start with a label, always end with bxlr. And we're going to BL into that right in the middle of here. Suddenly another task. A wild task appears. Okay, now this guy is going to do almost exactly the same thing. We're just going to load up Charles' word. It doesn't know what we're doing, and it's going to just behave as normal. It's not going to be doing exclusive loads and stores. Okay. I wonder if there's some way to actually view the exclusive store in the peripherals or registers or something, but I don't know. So we're going to do our normal thing. We're loading up exclusively, doing my add, and then my another task occurs. This goes and does a regular letter, subtracts 1 from that value, then does the store, then we BXLR back here, and then we do the store exclusive, and let's see what. So the store exclusive worked. So just doing a regular letter and a regular store is not going to give our exclusive load and store enough information about that this has changed. It's not going to affect our exclusive monitor. What if I do in here a letter X and stir X? Zero. Oh. So I'm just doing a basic exclusive load and store pattern, loading it up, changing a value, putting it back in memory. Then I'm going to compare to 0. And then if it's the store fails, I go back to try it again. Okay. Exclusive load, add 1. I end up in this other task, load another memory address, do another exclusive load, subtract 1, exclusive store. That worked. Then it goes, returns to the other code. Now I do this exclusive store. Uh-oh. And the result was 1. So it didn't actually manage to do that store. So I should end up in the failure loop. And I did. So the exclusive store failed. I guess I would wonder now, I want to make sure that I know exactly what has happened with this. Oops. I want to make sure that I'm not, I want to make sure I know what happens in memory. So we'll just have a look at that. I'm going to make this like 3, so I'm not going over the same same values. Okay. So I'm putting something in R1. I'm in my other task. Should be taking these 4 bits from memory. So it stores that FF into memory. So far, so good. That decided it was successful. It comes back. And now I'm going to try to store this. This should fail when I try it, and it should not store 1 in memory. So it didn't store 1 in memory. Memory hasn't changed. And we got a 1 as the answer. So we know that that store failed. I'm still changing the memory address it would store to. Because they're both loading the same word of memory. That's why I didn't bother changing that. I can change it and I don't think it will make a difference. Now I'm doing the store. It did not store, and it gave me the failure signal. What happens if the second letter X is offset by 4? Good question. I'm going to go use my second one. I already have, I handily already set up 2 little words in memory, Charles word and Charles word 2. Charles word 2 is sitting here. So in this time, I'm going to try doing an exclusive load from this address in memory, doing the letter X and the stir X here. Any predictions about what will happen now? Is this going to work or fail? I'm going to step through it and we'll find out, and you can pop your predictions. I should have done some kind of quiz, right? Will this work or not work? So the first one is loaded, adding 1 to R1. Now we're in my other task. I'm doing some work on different memory, but I'm also using letter X and stir X. So I've updated that second word in memory. That stir X worked back here. Now I'm going to do the outer stir X, and it failed. So Gabe was correct. It didn't succeed, returned 1. And this sort of shows us now that we really only have the one bit of information. So you can do a letter X and stir X in one part of your memory, and wherever, if you do another letter X and stir X anywhere else in memory, it doesn't care where it is in memory, it's still going to mess up that exclusive store. Now we can do an even simpler task that will ruin this for us. All we have to do is use the clear X. In fact, I don't even need a task to do that. I can just have that single instruction in my letter X stir X, and it would still fail. BL a simple task. So I'm doing exclusive load, that's all good, adding 1, going to my simple task, clearing the exclusive monitor, coming back here, and then trying the store. That's failed, didn't do anything, and we end up in the failure loop. Yeah. So I think we're starting to clear up our confusions, right, about how this works. It's possible to build up all of these complex synchronization patterns, mutual exclusives, locks, semaphores, using these very basic building blocks. But it's a very basic mechanism that allows us to do this. It's clever, isn't it, that we can get away with something so basic and it will work. We can get away with it, I guess, because we have only a very limited CPU and we don't need to cope with a lot of synchronization problems. But if we are clever with these simple ideas, then we're not going to change anything. One more question. Adam has asked, what happens if we only use exclusive load in the simple task one? I think that's going to work, and it's not going to change anything. So getting rid of the clear X, I'm going to put letter X in there. So I'm doing an exclusive load, and then I'm doing another exclusive load. So I think, I mean, you can tell me your prediction. I've got my prediction in my head about what's going to happen. Doing my exclusive load, adding 1. Now I'm in simple task, doing another exclusive load into R3. And it works. We put the correct thing into that memory. R2 is 0, so our store was a success. And we end up in the success loop. So letter X only ever sets things to exclusive, and it doesn't check what happened before. So I guess it's up to us as yeah, that's not quite true. Nope. Letter X is only 1 bit. Sorry. The monitor is only 1 bit. Yeah, when you do a letter X, it sets that monitor to be exclusive. We don't care what the address was. So the Sturex has worked either way, yeah. So what this shows us is that we did an exclusive load from Charles Word, and then we did an exclusive load from Charles Word 2. Then we did an exclusive store back to the original Charles Word, and our system was not able to know that we had in between done a different exclusive load. So it doesn't care about, in this level, it doesn't care about the actual memory address. It just cares that we've set this 1-bit monitor to be exclusive. And that might seem limiting, but we have to keep in mind that this really only becomes a problem for us if we have some context switch to another program. And whenever we have a context switch, we have an interrupt handler that calls it. And whenever you have an interrupt handler, you end up with clearx. So the interrupt handlers always call clearx. So whenever you have an interrupt handler, all bets will be off in terms of any exclusive monitors. They'll all be set to open. Of course, your second thread may do a bunch of exclusive loads and stores, and maybe it will get interrupted in the middle of them. Then its exclusive monitor will be opened again. Your original thread will go back, and where it expected the exclusive monitor to be set to exclusive, it finds that it's now set to open, so the Sturex will fail. And this allows us to do everything we wanted, all of our semaphores and mutexes. What happens if I try to do a Sturex to a different address to where I literexed? That's an excellent question. I'm having chats with the tutors now. I'm going to get 2 addresses. The question is, what happens if I try to store to that one, load from this one, and then store to that one? My prediction is it won't notice. Oops. Literx from this one, store X to that one. It works. We stored into a different one than we'd loaded, exclusive stored to a different memory address than we'd loaded from. Ryan Rashid says, what's the use case of these exclusive instructions? I think I gave about a 90-minute lecture on Friday about all of the use cases for exclusive instructions. The use case is to define higher level synchronization systems, some kind of lock, so that you have confidence that when one program accesses some shared memory, then another program can't access that shared memory without knowing that something is going wrong. So if you've got 2 programs running on the same computer, they're both sharing 1 bit of memory, they can't just both be accessing it and storing it at the same time. If they try that, they'll end up in strife. So you need to have some way to make sure that if you switch between 2 programs on your disco board using a context switch, that they'll realize that they've been switched out. And this is what literx and sturex gives us. Yeah, so that's all I can have time for about that today. I think you'll have to go back and see Friday's lecture to see the details about that. The lecture on asynchronism. And there's a bit more further reading about that if you want to get more into it. I think we're going to move into the networks phase of today's lecture. We've had enough fun looking at literx and sturex. Oh, great. So Ryan says that summary is exactly what I was after. I'm happy to help. I know that these things sometimes get a bit mixed up sometimes. It's hard to work out what the connections is. But something that I'm trying to do with this course is that whenever we have a high-level concept, we look at how it works on the disco board and see if we can make that connection. Gabe's just asked a really good question. Surely this falls down as soon as there are multiple tasks sitting, including the monitor. So here's task 1, and it's done a literex and it's set the monitor. I'm going to make myself big so I can try to get this right. Now maybe I'll make a blackboard. It's taken me ages to work this out. So like, we're all learning together sometimes. So here's task 1. And here's task 2. And we've got one exclusive monitor. Oops. Okay, so task 1 does a literex. And then this one wants to do a stirrex. So we're interleaved 2 tasks. This is time going forward, right? Time. So task 1 does literex. The exclusive monitor is tagged exclusive. Okay, now we have a context switch. So we go to there. That means that in between there we had clerex. So our exclusive monitor is opened. Okay, task 2 does a literex. That means our exclusive monitor is closed again. And then we get another context switch back here. That runs clerex as well. So our exclusive monitor is open. So now we try to do a stirrex in task 1, and that fails. Fails. Nothing changes about the exclusive monitor. Clerex happens, but nothing changes. Try to do a stirrex over here. The exclusive monitor is open, so that fails too. I think that makes sense. There's another option. What if we, oops. Try to rub out all of the chalk off my chalkboard. We're never going to get to networks today, never, ever. Well, in some ways, it's really mind-bending what's going on here, whereas the networks is a little bit more easy. So I'm happy to spend some time on this. Suppose we have task 1, does a literex, okay. So far, so good. That closes the exclusive monitor or marks it. Then we get the context switch, that opens it. We do a literex in task 2 and then a stirrex. Nothing happens in between here, so it succeeds. Yay, success. Smell of sweet success. Okay. Then we task switch back. That means we run clerex. So actually after the stirrex happened, literex happens, we mark the exclusive monitor. Stirrex happens, it clears it. And then we get another clerex. It's already cleared though, so it doesn't make a difference. Stirrex over here fails because it notices that it's cleared. So that should hopefully convince you that if just with this one bit of information, we can handle literex and stirrex. And of course, we don't use literex and stirrex by themselves. We use them in a little bit more complicated algorithms to define a lock, as we did on Friday, or define a semaphore, as we did on Friday. And if you have those things, then you can get yourself out of trouble, or most of the time. Yeah, Adam is saying this is incredibly clever. I think so too. And it makes you feel clever once you work out how it works, right? So everyone should be feeling pretty good right now that we've all gotten our head around it. Week 9, networks. We're only 45 minutes into week 9 and we're finally getting to networks. So this week's a little bit different where we're looking at some higher level concepts, basic concepts of networks, the kind of terms of reference that you need to know when you're discussing different kind of network systems. I'm going to give you a little example of a musical network protocol, and that will probably be what we do today. Then on Friday, we look at this so-called 7-layer model for how network systems behave, and layers meaning different responsibilities for different objects as part of the network, and then looking at some examples with standard protocols. And I say networks meaning, perhaps beyond just the internet, or we're not just looking at things like the internet or mobile phone networks or local area networks, but also any connections between different computers. That sort of comes into the definition of a network that we're using in this course. So whenever you've got two computers that need to talk to each other, or two components of a computer that need to talk to each other, there's some kind of way of getting that information between computers. So when you're outside the CPU, information's in the wild world, you need to talk to another CPU. This is what we're calling a network here, at least in this basic concept part of the talk. Basic concepts. So the high level view is we want to communicate with others. So far, you've done a lot of communication with the disco board. You've looked in memory, you've looked in registers, you've looked in peripherals to see the values of, or change the values of LED drivers. This week you're starting to read things from sensors, read the values of buttons on your disco board. And so far, the way you've done this is either by looking at information in registers or looking at information in memory. But we can't fit everything we want to communicate with as memory mapped registers or regular registers. We might want to talk to some other computer, and we can't have like the same kind of direct connections that we have with memory and registers to that other computer. So we need some other ways to communicate with these other computers to get information between them. So that's the concept of this lecture. How are we going to put information through different kinds of channels in order to make sure that other computers understand what we're saying and that we understand what they're saying? So what's difficult about this? Well, if both ends of a communication channel could share memory and registers, like you have two computers and they're both looking at the same memory and registers, then that would be great. We can have very easy communications. You would just leave a value in memory for a different computer to see, and then later on it comes by and says, oh, hello, there's this little message left for me in memory, and I understand what that is, so I can grab it. So, of course, you can do communication between different parts of your program, for instance, by using some kind of shared global variable. You could be putting a variable in the data section, and then your different functions could both be accessing that data, and then every part of your program will be happy. But most of the time, you're not trying to communicate between different bits of your different parts of your program. You're trying to talk with a different CPU. And Jackson's just made a really good point in the teams that, like, even within one computer, you will have different kinds of different processors that will have different roles. Like on video game consoles, you start to pull them apart and there'll be some main CPU which will be running a simple program, and then maybe they would have added a special one just for doing some graphics, or a special one just for doing some maths processes, just like in the old days you used to have co-processors to do floating point maths. or do some special maths to do with colors. So there's this idea of adding coprocessors to make your computer more powerful. Then you have to have communications between them. Yeah, actually, so I guess Jackson's point is that the color math processor probably shares area of memory, so that would be called DMA, direct memory access. But we're talking about when you can't do direct memory access. Is that what DMA stands for? I should probably look it up, but I think it is. I'll look on my other screen, so I'm not. Yes, direct memory access. I'm not wrong. Thank goodness for that. Now, when we look at a screen like this, we've seen this before. This is our memory. Can we see where any of the data structures are, right? I've asked you this question before. And we can't really, because we've got a bunch of bits. We don't know where everything starts. We don't know where it stops. And it's unclear what where the structures would be and what could be possibly happening. Now, the problem that we come to when we're trying to talk to another computer is that for instance, if we connected one wire, we wouldn't even be able to see where the bits are, because like if we just see this voltage on a wire, we don't know if it's a 1 or a 0 or what. We have nothing to compare it to. So all of our contrasts that we would have seen in our memory disappear when we are outside of our computer. So at a kind of higher level issue, in order to send some kind of data, then our two computers that are talking to each other will need to see some differences in signals that are occurring. So I can't just be sending you the same signal over and over again. And then it would be equivalent to that white screen where all of the contrast is gone. So we need some kind of difference in order to understand that there's data within a signal. And this sort of starts to touch on information theory, which is a whole subfield of maths. If you're interested in information theory, which you probably should be, you can go and take a course in second semester. And if you're only a little bit interested, you can do some reading about it as well. But for the main point here is that data requires some kind of contrast or difference in order to get it. So the question now is like if you have a wire connecting two computers, this wire will carry an electrical signal. What might difference look like, and how many different ways could you achieve it? I guess this is a bit where we have to do a bit of a chat, but I want to just keep moving to get to the more fun bits of the lecture. So we might think you've got some kind of wire, right? And actually you really need two wires, don't you? Because you always need a ground and a not ground wire, ground and a signal wire. So our ground wire is going to be the one we compare it to. That'll always be 0 volts. And the signal wire could have some voltage, n volts. And I guess what we can do is make a graph of the voltage of this signal wire over time. We've started talking about electronics now. How did we end up in an engineering course? I'm not sure. And don't repeat that to the engineering lecturers, because they'll ask me to explain what I'm talking about. So we've got just a giant list of things from Gabe, who knows more about me than different kinds of signaling on a wire. RF takeover indeed, yeah. Let's just think really simple about it. We've got our voltage graph. This is time. And that's going to be like some positive voltage, let's say 5. So our signal on the voltage wire could be going up and down, right? And we have to try to work out some way to make sense of these ups and downs and turn them into a signal, which is useful. So one way we could do it would just be to say, well, when the voltage is 5 volts, then that's going to be a 1. And when the voltage is 0 volts, that's going to be a 0. Another 1, another 0. Are there any other ways we could do this? We could also, could we just look at the changes instead? I mean, the problem with this is that how are we going to do 1, 1? I want to have 1, 1. It's just going to have to be like maybe some kind of really little 0. I don't know. Have to have something which is so little that it ignores it. In the chat, there's a suggestion that we might have to have some kind of clock. So we could clock these in. If we knew that we had our divisions, then if that was a 1, it would look in that and see 1. In our next clock division, we could look in that and see another 1. It could have changed here to be 0, so we look in there and see a 0, right? Maybe we could have the shift be the change, so it could be that shifting from low to high in here gives us a 1. Then we quickly go low and do it again, shifting from low to high, and then we shift from high to low, right? There's lots of different ways that this could look. There's many different ways of achieving this, but we basically have to find some way of understanding changes in a voltage over time as ones and zeros. And I think it should be clear now that there's lots of ways of doing it, first of all, and maybe it's not that simple, because if you don't know what you're expecting, then you can't tell where a 1 ends or a 0 ends. So there's 3 aspects of network communication that I want to talk about today. These are the fundamental aspects. So the first dimension, I say, would be like the transmission medium. So what is it that you're sending your messages through? What medium are you sending your messages through? And so far we've been talking about electrical signals, but we'll discuss a few others. Another aspect of this would be communications protocols. So that's the information that both ends have agreed on in order to make sense of a message which is being sent across the wire. So part of the communications protocol is even knowing which thing going across the wire is a 1 and which thing going across the wire is a 0. And then at a higher level, the protocol will be saying, well, now I've got these 1s and 0s, can I interpret this as a byte or not? And how do I know when a message has ended? And how do I know if a message was correct and not corrupted halfway through? So there's lots of aspects of protocols to be discussed. So the third one I want to talk about today, another basic dimension, is topology. So if we've just got one sender and one receiver, that's going to be a very simple situation. It gets more complicated if they both want to talk to each other and receive information. They want to be both senders and receivers on both sides. Okay, that's one topology, just one-to-one. Now, what if we have lots of senders and receivers all around in a network, and they're connected to each other in different ways? So now our network connections have some kind of shape, so that's why we get to topology. Now, these 3 aspects are kind of at least partially orthogonal or independent of each other. And there's something that in this course, that'll be how we kind of categorize or characterize different kinds of networks. So first of all, let's just get basic. What's a node? So a node is anything which communicates on our network. The node could be a computer, it could be a mobile phone, it could be your fridge, some kind of IoT device. It could be a nanobot, which is going to work together in your body to solve bad problems. And you can see that sometimes nodes are going to be kind of big, important, expensive things like a computer, and sometimes they might be something which we don't care much about, like an IoT device. Like all my light bulbs in my, my office are nodes on a little network so that I can turn them on and off automatically and set them all to the right brightness to do my lectures. Of course, each of these light bulbs is not very expensive and not very complicated, but it's still a network node. What about transmission mediums? So we've talked about electrical voltages on a wire, one wire, or several wires, but there's lots of other options for media for transmitting network messages. We could have coaxial cables, for instance, that's a regular wire. We could have twisted pair cables, a different kind of electrical wire that we use for regular local area networks. We could have electromagnetic waves in the air, another popular transmission medium for sending messages in our everyday life. We could have light and an optic fiber cable. That's a transmission medium which many of us would wish we had more of around our houses, but or in between our houses, but we don't. We can also have kind of wacky transmission mediums, which are useful, potentially useful, sometimes a joke, sometimes get people out of sticky situations. One of the an amusing joke was TCP over avian carriers. This was an April Fool's joke someone sent in 1999 to the request for comment. So this is where you organize online. People are organizing different protocols for working with the internet, network working group. Oops. So someone suggested this, IP over avian characters with quality of service. So it would be an experimental protocol for the internet community. And you would use an avian carrier, aka a pigeon, to carry your messages through the air. And they've done quite a bit of work here to make sure that it's going to work. Avian carriers normally bypass bridges and tunnels, but will seek out wormhole tunnels. When carrying web traffic, the carriers may digest spiders, leaving behind a more compact representation. The carriers may be confused by mirrors, so there's obviously some some tricks here. Round robin queuing is not recommended. Well, you can read more about IP over avian carriers later, but that's another potential medium. What about some normal ones? We've got our copper wires, we see them every day. Fiber optic cables, that's not really a fiber optic cable, but it kind of looks cool and could represent them in some way. We could have waves in other mediums like water, like sort of pounding the earth to create, to shake the earth in a certain way and create waves that way. So I know we've got electrical engineers in the room, but for those potentially who are a little bit confused, maybe haven't studied physics or electrical engineering, a voltage on a wire is a relative measurement. So you can measure one wire and another wire and say, well, this wire has more potential energy than the other one. So what we're really measuring is voltage difference between two wires. One we call ground and one we call the signal wire. So the ground pins on your disco board, you might have looked on your disco board and seen that there are little labels on it, and some of them say GND for ground. So they're the reference point for all of your voltage measurements. So if you wanted to send a signal to your disco board, you're going to need to have two wires, one connected to ground so that your reference is matched on either end of the wire, and one connected to the signal pin that you want to talk to, one of the GPIO pins that we talked about in the lectures last week. So sometimes when we're sending signals, the values matter, right? Whether you happen to have a high voltage or a low voltage. And sometimes the transitions going from low to high or going from high to low is going to be what matters. Now we know last week that when we wanted to know when someone clicks the button on your disco board, we weren't looking for a high value. we were looking for a rising trigger, a rising edge. So we can certainly use rising edges to recognize communication. You could be doing Morse code through the clicker and recognizing that on rising edges. Oop. So remember that right now we're still talking about digital information, just 0 and 1. I think I'm not going to talk about any other non-binary, non-digital information. We're just talking about zeros and ones in this lecture. Someone's eyes hurt because of the RFC document I showed you. We have to make sure that we're clear that even though this voltage could be anywhere between 0 volts and infinity volts, we're not able to, our computers don't care about that particular number, they just care about whether we interpret a change or a certain voltage as being a 1 or a 0. Now we're going to have some fun. We're going to do a little network demo just between us. Normally in our lectures we would do throwing things around the room to do this demo, but I thought we might do it just with reacts. So I'm going to open up Teams over here. I'm going to make sure I get to the bottom. And we're going to do our React net. I'm going to speak while I'm doing it, but everyone in the internet is a few seconds behind me. So I'm going to do React net. Now this is actually, I'm trying to get a startup together. I'm trying to organize a new RFC, a new way of sending messages across the internet. I thought it would be handy if within the regular internet, we could have a sub-internet where we're sending messages just with reacts. So I need everybody to help with my startup concept. So I'm going to send out a message to everyone. The way it's going to work is that if I have a smiley react, that's going to be a 0. And if I have a ruffle react, then that's going to be a 1. Okay, so I'm going to send a number out to everybody, and I need you to tell me what number I'm thinking of. Right? This is just a test to see how it works. So smiley equals 0, and where's ruffle? Oh, there it is. Ruffle equals 1. So tell me what number I'm sending. I've sent it out to everyone, and we'll see if we can get some responses. I've sent out 0011 to everyone. We got a lot of responses here. Okay, so I'm going to have a React survey. So React survey, we're going to have a sad face for, oh no, we're going to have penguin for 3, and we're going to have polar bear for something else. I'm trying to work out a good way of doing interactive teaching for classes on chat. I think this might be working. I wish I could make my font a bit bigger here. Maybe I can go in here. Ah, Zoom. That's going to work better. Cool. So I've sent my survey. They have to. Oh, you can't do custom reacts on the thing. Gotcha. So we've got a lot of 3s. Now, the problem is, and I don't want to blow everyone's mind, but I was really not trying to send you 3. I was trying to send you something else. What was I trying to send you? Ovi, what was I... Yeah. I was really trying to send something else. I think, Obi Simons might know, Maybe Josephine? Oops. I'm in the... Jackson's kill range says it's all relative to interpretation. So I sent 0011, but I'm really sorry, I was sending it to you in little endian format, right? So I was really thinking about 12, 8, thinking I was sending you the zeros column first, then the ones column, then the twos column, then the fours column, then the eights column. So I was really trying to send 12, but I didn't tell you it was little endian. So that's a real bummer. I'm really messed everyone up. I'm gonna have to go back. And Obi said, well, what about some kind of start or end bit? Maybe, how am I going to know when a message is over as well? Oh, maybe I'm still sending the message. It could still be, it could be that there's another crying or another ruffle happening, right? Darn it, Charles. Yeah, sorry everybody. I know I didn't give you enough information for my network system yet. ReactNet so far is a failure. So we're going to try something else in a minute and see if we can get there. But for the time being, we don't have enough information really to define how this network's going to work. Okay, I'm going to give you a few more slides. So if I say knock knock to everybody, if I say knock knock, I think more or less everybody knows what's going to happen, right? I'm going to have two screens here. It's streaming both at the same time. If I say knock knock, yeah, so Mitchell's got it. Mitchell says, who's there, right? So we all know this joke. If I say knock knock, you say who's there. It's a classic. So what I'm getting at here is that we have certain kinds of sequences of information that we expect to get. And come in is another one. And in networks, we call this a communications protocol. So it could be that our communications protocol is some agreed upon set of rules about what we're going to say and how we understand that information when it comes back in the other end. So this is where a lot of the difference between different communication networks are, and a lot of creativity and innovation. What kind of agreements are we making about what information is going on over the network? So there's lots of potential parts of protocol, but in our case, we can think of protocol involving how many wires are going between a sender and a receiver of messages, right? It could just be one wire. It could be lots of wires. We could be interested in how big the messages are, what information is being sent in these messages. Are we sending LSB first or MSB? Are we in little endian or big endian format going across the wire? Once we actually get the bits on the other end, what do these bits mean? Are they interpreted in the standard computing way, just as your disco boards interpret them, turned into 32-bit words? or are they interpreted in some other way? So communication protocol, it's sort of independent of the transmission medium. You can certainly have protocols which don't involve the media, but sometimes they do. I guess if we're considering how many wires to be part of our protocol, that's part of the medium as well. I guess we normally do a bit of a chat here, but there's times in life when our social protocols fail, and that often causes us to be embarrassed, right? In fact, but possibly that's like entwined with the way the meaning of embarrassment is that some kind of social interaction has failed because you misunderstood a protocol or you got something confused, and you end up with red face. So one instance would be if, like, you're walking down the street and someone says, you know, hey, how you going? And then you say, oh, you too. And you thought that they were saying like good morning or good to see you. And in fact, they were saying, asking you how you're going. So you've mixed up two of the greeting protocols. One is, hey, how you going? Pretty good yourself. And the other one is, good to see you this morning. And then you could say, oh, you too. So people do say, make every joke I make as a social protocol fail. In fact, there's some knock-knock jokes, like the one about the, I'll tell you the knock-knock joke. It's a bit hard to tell over the internet, but if I say knock-knock, and you would say, who's there? And then before you said there, I would say, moo! No, I've got the joke wrong. That's embarrassing. You have to say the joke correctly for it to be a correct social protocol. I say knock knock. You say, who's there? And I say, interrupting cow. And you say, interrupting cow. And I go, moo! Because the cow interrupts, right? So I've interrupted the knock knock joke procedure, which is why it's funny, because it's breaking the protocol in some way. Now, this is a terrible knock knock situation. I'm going to play along with this. Who's there? We're going to tell knock-knock jokes in the teams. Where are we at? How far am I getting in this lecture? Oh, I've got a little bit to go. Cool, we can get there. So a few important points about networks. One would be whether this protocol is circuit switched or packet switched. So circuit switched means that each of your nodes has a dedicated connection to every other node. So if I've got a computer over here, Mitchell's got a computer there, Oscar's got a computer here, and I've literally got one wire to go to Mitchell's computer and one wire to go to Oscar's computer. So in ye olden days, to route phone calls to the right place, the switchboard person would literally plug a wire between your phone and the other person's phone. So it would be actually making an electrical circuit between those two phones. And there's an example in labs next week, actually, where you start to connect your disco boards up, and you're actually making circuits between two disco boards that then define the network. So this is telephones in the old days. They've got all these little holes connecting to different places, so you can literally make a circuit between different phones on the network. Our other option, these are options for how to communicate with lots of different nodes on a network. First option was circuit switch. We've got making dedicated electrical connections between them. The other option is packet switching. So that means that we've got a network which everyone is connected to, and then there's packets or frames of information going along that network. And each packet itself doesn't just contain its own data, but it contains some kind of address. So the packet will know itself where it's supposed to go and then trust the network to get it there. So packet switching is the way most of our networks work, right? The way the internet works, the way your wireless LAN works, the way your regular old LAN cables, blue cables around your house will work. packet switching is the one that is most useful. So this means that lots of different nodes can share the same physical connections. You can have a lot of wires in your house, and every computer in your house is going through one phone line to the NBN, and then there's a big fiber optic cable taking everyone's phone lines from the little local box to the ISP. So we're sharing one physical connection with lots of packets going along them. So now we're going to do ReactNet v2. So I want to start to open up the idea of a packet on our network. So in order to have a packet, I'm going to need to have another ReAC. Go down to new messages. Interrupting sloth who? Trollolol. Let's do packets. Network now. So this is going to be easier. I'm going to be a little endian format, and we will use a to mean end of message. Okay, so I've got changing my idea for my startup for ReactNet. I'm now going to be communicating in packets, and that means that I need to know when the packet starts and ends. Okay, so in between each packet, I'm going to have a thumb, and I've still got my existing system, which was just a smiley face equals 0 and a ruffle face equals 1, I think. That was how it worked, right? Yeah, smiley 0, ruffle 1. So now I'm going to do this one. Let's see what we get. Smiley, ruffle, smiley, ruffle, ruffle. Okay. So what am I sending? I've just sent a little ReactNet message, a ReactNet packet across my network. And we got 26 from Oscar. So let's see, is that what I was thinking? I'm just going to decode it now on my, not that one, I want to be on my slide. So my message was 01011 and then packet over. So that means that's going to be 0, that's going to be 2, 0, 8, and 16. So it should be 24 plus 2 is 26. Yep, Obi is just... Obi's just asked me if this means we have base 3. We have a lot of reacts, so this could have very high base. This potentially is going to be very complicated from an information theoretic perspective, but you know, we just have to make a minimum viable product, and then we'll deal with the uncertainties later. Okay, we got a few. Thanks, base 17 going rise up. A few more network concepts, then we might try to extend our system again. What about directions of information flow? So far, I've just been sending information one way from me to you, simplex. That's what that means. If I had some way of sending information one way or the other way, but not at the same time, we would call that half duplex. And then full duplex means that information can go both ways simultaneously. So if we have a mechanism where maybe we have one wire which is going to be the signal in one direction and another wire where the signal is coming back, then that would be full duplex, because we could just be using both of those wire mediums simultaneously to send wires. But we might be able to work out some way with ReactNet that I could say not just that's enough information in the packet, but now I'm finished talking, now you get to go, and then we could have information going both ways. So it's like when you have radio protocols, right? Like on walkie-talkies. If someone says over, then the other person can speak, because there's only one radio frequency and you're both speaking and sending and receiving on the same frequency. So if you're both trying to speak at the same time, the signal will get mixed up and the radios won't be able to decode it. But if someone says their message to the person at the other end, and then at the end they say over, then the person at the other end knows that it's their turn to send a message on the same frequency. Now, this is starting to reference some network protocols related to that you're going to implement. And you're going to do one in assignment 3. I'm going to talk a little bit more about it on Friday as a preview of assignment 3. We haven't quite finished with assignment 2 yet, so we're just going to keep things a little bit relaxed there about talking about assignment 3. But in assignment 3, you are doing a network protocol on the disco boards, between two disco boards, or maybe just from your disco board to itself. And then the last little concept for the day, topology. So topology is going to be the way that all the nodes on your network are connected, right? And this is going to be both physical connections and logical connections. There could be differences between those. So there are several different ways to connect nodes together. They might have pros, they might have cons. You could have here's a few examples. One would be just to have one big wire and all of your nodes are connected to that wire. And that would be called a bus topology. You could also have each node on the network connected to its neighbors or to two others in some sort of ring like this. They could be that all the nodes are connected to one person in the center. That would be a star topology. So let's have a think about the complications here that could happen. If you have the star topology and this person over here wants to send a message to this person, then they really have to send a message to the person in the middle. And the person in the middle then needs to decide who gets that message. Shouldn't send it there, that would be wrong. So the person in the middle is responsible for kind of knowing what the addresses are of everybody else in the network, and then they have to send it to it. On the other hand, if someone runs out of batteries, then our network doesn't break. Or if one of these gets destroyed, the network's still going to work while this person is still working. Suppose we have a ring topology. Well, you really just sort of need to know who you have either side of you, and then you can just keep passing a message around. So you've only got two options. Either you can, if this person gets a message, they know it came from this person. There's no use sending it back unless it belongs to them. Suppose it's supposed to be for here. There's no use sending it back. They may as well just send it forward on the network until we get all the way around the ring. So this one's kind of more simple because no one has to be the leader and know who everyone else is on the network. We just have to keep passing messages around until someone's like, oh, that's mine. Stop moving it around. But one complication here is that if the network cable gets broken or eaten by a mouse, or someone puts a shovel through it, then our ring topology doesn't work anymore. And with the bus topology, This one's probably the simplest because supposing this person wants to send a message to this guy, they're just going to put the message on the wire. Everyone will hear it. And then it's up to each individual node to either pay attention to it or not. So if this person at the end knows it's for them, they can act on it. All these other people are just going to ignore it. They don't care. Problem with this one is that everybody on the bus is going to have kind of somehow work out that their addresses should be different. They're going to have to work out their names and make sure that they don't clash. So it's going to be a little bit difficult to keep track of it. When you send messages around your local network, right, you've got something called a router, probably does your Wi-Fi as well as handles your internet as well. The little box you get from your ISP. And that little box has a responsibility of finding everybody on the network and giving them an address. So everybody on a network has an address for the actual hardware that's connecting, either a wireless card or an Ethernet card. So I've got a what's called a MAC address, the hardware address. And then your router is going to work out who's who and give them a new address for sending internet protocol messages. So that's just a little about topology. We'll talk more about it on Friday. Now we finally get to ReactNet v3. I know you were waiting for it, but I want to send a message to a specific node. So let's do a bit more React. So I'm going to pick on some people. To pick on, I'm just looking through some people I haven't heard before or who I know are in the chat. Jiajun Lu, if they're still there. At Jiajun, your address is gonna be and then Josephine Josephine's address is going to be okay. So now this is going to be a little bit tricky, but I'm going to send a message to the person at the middle of the star topology, and I think that's going to be Jackson. Sends a message to the person at the middle of a star topology, and the message is going to be thus at Jackson. It's going to be, now we get tricky. We might be starting to see the cracks forming in my network because I have to remember a lot of things. What was the ending? Oh, it was a thumb. So we'll see if Jackson jumps in and routes these packets. So what I've sent to the network is cool glasses, smiley, smiley, ruffle, thumb, crying, ruffle, ruffle, smiley, thumb. So what I expect to happen is that the cool glasses packet ought to get to Jiajun, and the crying with laughter packet ought to be getting to Josephine. We'll see if it actually gets there. We got one routed to Jiajun. What about the other one? Is Josephine still online? Maybe she's gone. Oh, there we go. Oh, thanks. Thanks, router. So now, whenever I send a message in ReactNet, the person who's going to be the router at the middle of the network, I have to make sure that they're online, and they're going to have a list of who each React belongs to, and they're going to send the Reacts to that person, at them. So this is a way that our network protocol, I guess, could jump between, for instance, Teams and Messenger. So Josephine got the message. So this is the first successful routed message through ReactNet. This is a historic moment. First successful message through ReactNet. I'm sure this is going to do great things for sending messages, having a meta internet sent through the different chat systems. So if someone's in Discord, they could be doing their Reacts there. Someone could have both Discord and WhatsApp open, and they could be relaying messages as Reacts through that, making sure that they get routed to the correct address. We could have someone who does network address translation, so they might have a list of all the people, all of the connections that certain nodes on their network have made, and then when they're sending their Reacts, they can convert those Reacts to different Reacts which are on the outside of that subnetwork. Oh, this is great. So great. Okay, so now finally we've made it to the end. I'll leave you with this question. I'll leave you with this question. Now that we've had a lot of fun this lecture, playing with a little network system, doing some topologies, doing some packets, doing some routing and addresses, I'd like you to think this week about whether there are any network protocols dedicated to musical instruments. And we'll discuss this on Friday. But it's, we've talked a bit about how musical information is stored already as part of our assignment prep. But I really think that there's other systems which are more about transmission of information, which changes our focus on some of these things. So you all have a think about that. I'm just going to remind everyone, I think that everyone who's here in this chat is well aware of the fact that we have an assignment due on Friday evening, the sequencer assignment. For everyone out there watching my lecture, make sure you put a great effort into this assignment, particularly your design document. I think the tutors, it really hurts their soul if they have to read a lot of design documents. When they read ones that haven't had a lot of attention put into them, it hurts them. And I want to, help their emotions and their resilience in this difficult time. And the best way that you can all do that is by writing really excellent design documents. So go and look at our advice on the website about how to write a design document. Show them your design documents and show them your assignment ideas in the assignment help sessions. There's one today at some time, and there's one tomorrow at a different time. They're both in the afternoon. I've forgotten the exact times now. One starts at 2 and one starts at 4. Can't remember which is which. Make sure you get your assignment in. Now, crucial information is that assignment 3 is going to be starting very, very shortly after assignment 2. So in fact, as soon as you finish assignment 2, we'll release assignment 3. So that means you need your jumper wires. I've said this for weeks now. You need these little wires to connect your disco board to itself. You can't do the lab next week unless you have jumper wires, and you can't do assignment 3 unless you have jumper wires. Getting jumper wires is your responsibility. Make sure you get them. No one's been upset on Piazza about jumper wires yet, so I have to assume that everyone is fine. They have their jumper wires and they're completely happy, which I'm not quite sure is the case. I really need everybody to get their own jumper wires and make sure they're ready to do these assignments. Sorry, Mitchell is correcting me. We do not have a assignment help session this afternoon. We have one on Wednesday afternoon and Thursday afternoon. Wednesday at 2 o'clock and Thursday at 4 o'clock. That said, if you can't go to those times, go to a lab, go to any lab, go to labs right now. Sit in the labs channel and keep adding tutors during the day, of course, and people will be around. Tutors are willing to help you with whatever problem you have during lab times when they're online on Teams. Just head into the labs channel and see if there's anybody there. There's lots of times when you can find tutors online ready to help you. We all want you to do well, and the best way that you can do well is to talk to us about what you're doing, and we can give you great advice. So for that's I think enough for the day. I think I might go to the outro screen. I'll say goodbye. I'll see you all on Piazza and Teams and catch up with you again on Friday. So thanks for today.